Shown in the figure below is a scene from a filthy bathroom. As the roach clings to the paper, its weight causes the paper to unwind and the roach to move towards the floor. Treat the roll of paper as a solid cylinder of mass M is 0.2 kilograms and radius r is 0.15 meters. Treat the roach as a point object of mass equals 0.1 kilograms. A, find the moment of inertia of the paper, and B, find the velocity of the roach just before it hits the floor. Although the picture in this problem has many more details and is much more gross, this is exactly the same problem as the bucket going into the well, and we'll solve it by exactly the same procedures. It is amenable to both force and energy methods. However, since we're asked for velocity after falling a distance, we'll be using energy methods. And we begin by identifying the two moments. One when the roach first lands on the toilet paper, and the second just before the roach escapes to skitter across the floor. We'll connect moment 1 to moment 2. And since we've selected energy methods, the first question we ask ourselves is whether there is any work due to a non-conservative force. Since we assume that there's no friction between the toilet paper and its holder, we'll say that there is no work due to non-conservative forces, and therefore this problem will be solved by conservation of energy. The conservation of energy equation is realized by setting the total energy at the first moment equal to the total energy at the second moment. We'll begin with moment 1 and ask ourselves 4 questions. At moment 1, is there translational kinetic energy? The answer is no. At moment 1, is there rotational kinetic energy? The answer is also no. At moment 1, is there gravitational potential energy? The answer is yes. The roach is 0.7 meters above the floor, and taking the floor to be the height of y equals 0, this will lead us to a gravitational potential energy term of mass times g times y. There are no springs, and so we have then completed the total energy term at moment 1. Let's set that equal to the total energy at moment 2. Asking ourselves the same 4 questions, we find that, number 1, indeed there is translational kinetic energy at moment 2. This is 1/2 the mass of the roach times the velocity of the roach at moment 2 squared. There is also rotational kinetic energy at moment 2. This will be of an amount 1/2 moment of inertia times angular velocity squared. There is no longer any gravitational potential energy since the roach has reached the floor, and there's still no spring. In this equation, we will eliminate 2 rotational terms. These are the moment of inertia and the angular velocity at moment 2. Since we are approximating the roll of toilet paper as a solid cylinder, the moment of inertia will be 1/2 the mass times the radius squared. Even though I've been given the radius, I recognize that this radius will cancel out. However, since we were asked in part A for a numerical result for the moment of inertia, we can go ahead and plug in the radius of 0.15 meters to get the result 0.0056 kilogram meter squared. To address the angular velocity term, we recognize that the toilet paper unrolls, and therefore the linear velocity of the roach is directly related to the angular velocity of the toilet paper by v2 divided by the radius. When I plug these terms in, I'm going to leave the radius as a variable r, since I anticipate that this will cancel before the equation is done. As anticipated, the 2 factors of radius from the moment of inertia cancel with the 2 factors of radius from the angular velocity. We can pause to think about why that must be true for a moment. Since kinetic energy will always be in joules, mass times velocity squared has the same units as moment of inertia times angular velocity squared. And this is why when we plug in the moment of inertia containing mass and the angular velocity in a form that contains v, we expect that the radii should cancel, or at least appear in a proportion where their units will cancel. On the right-hand side of the equal sign, we'll have 0.05 v squared plus another 0.05 v squared for 0.1 v2 squared. The 0.1's cancel, giving us the final result, 2.62 meter per second.